So we're going to be talking today about collisions in 2 dimensions. And a lot of what we're doing is going to be exactly the same as what we did in 1 dimension with head-on collisions. There's only one thing that will change, and that is that all of our vectors now have to be represented with x and y components. And along with that, the specialized equation, velocity plus velocity equals velocity plus velocity, now no longer applies. Which is why I didn't really teach it to you guys, because it only applies to limited circumstances. Yes?
Is the 2D collision going to be this
You could be. You'll see the stuff that we do with it is pretty easy. Yep. So here's our setup. We're going to have an object M1, another object M2, and M1 is going to head towards M2 with an initial velocity, and I'm going to label that velocity as V1, comma initial. I can always choose a reference frame so that M2 is standing still. Specifically, I can choose M2's reference frame. So almost always, I'm going to represent the initial velocity of M2 as 0. That just makes my life easier. Now the two of them are going to hit. And when they hit, then they're going to bounce off of each other. If they stick together, then what I have is a totally inelastic collision, right? And since momentum is conserved, I know already that the whole thing is just going to go in that direction. So the totally inelastic collisions can't be 3-dimensional or 2-dimensional. They have to be 1-dimensional between 2 objects. Well, is that strictly true? It's strictly true as long as my... Think about this. Velocity 0 goes off that one. That's because its velocity in that reference frame is that one. Yeah, so as long as I'm taking the reference frame so that this velocity is 0, then the totally inelastic occur in 1 dimension. So there it is. But for partially elastic or totally elastic collisions, there will be some kind of bouncing. And when there is a bouncing, then we're going to have V1 final, and we're going to have V2 final. And the key thing between these is the angle between the velocity vectors. We measure that angle theta, and theta is called the scattering angle. And the scattering angle gives us some important information about the percentage of energy that is lost in the collision. From 0 to, can't be 100. Can't be 100. Notice how I've labeled these. V1, comma initial, V1, comma final. V2, comma initial, V2, comma final. Okay? And now our task is going to be to find V1 final and V2 final. And our tool for the job is going to be conservation. Specifically, conservation of momentum. And honestly, conservation of momentum is going to carry us through all of the problems that are in your homework. Sometimes, if I am not given enough information, but I am told that the collision is totally elastic, then that would be enough information to find both final velocities as well. But I don't think you have any problems to work like that. The algebra there gets kind of yucky because you get quadratics with substitutions. Okay. Now, in AP Physics, we deal with this case, and we introduce some additional vector tools that make life a little bit simpler. Is there a question? No. Okay. What I'd like to do is to take a look at now at number 40 as an example of these kinds of problems. And on page 190, number 40, what we are told is that we have a nucleus that is at rest. We're not told what kind of atom it is, so we don't know how heavy the nucleus is.
I didn't know that having to be at rest? I thought it was always vibrating.
That is correct, however, the vibration is primarily the electron. The nucleus will also vibrate some, but it usually is vibrating negligibly compared to the electron. So most treatments of quantum mechanics assume that the nucleus is at rest. If you don't want that to happen, then you have to do relativistic quantum physics, and it gets to be a pain in the neck. Okay, so we're looking at number 40. We have a nucleus, and it's sitting there. Ain't that nice? Immediately, we can do our before situation. What is the total momentum of our nucleus before anything happens?
Zero.
Zero. That's right. Then a radioactive event occurs. The reason for this radioactive event is really, really interesting. It's actually called quantum tunneling. What happens basically is that the strong nuclear binding force holds the nucleus together, and that strong nuclear binding force presents a barrier to any objects falling apart or leaving, which is good, because the nucleus has a lot of positively charged particles that repel each other, right? So without the strong nuclear binding force, then all of our atoms would go just like this. But there is a strong nuclear binding force that holds them together. And it is the case that for very small energy barriers, such as the one presented by the strong nuclear binding force, that objects can actually, quote, tunnel through that force, really the potential energy barrier that's presented by that force. In other words, they can sort of spontaneously appear on the other side of it without actually going through the intervening space.
So they basically teleport.
It's basically teleport. That's exactly right. And that process actually happens all the time. It happens in electrical conduction when you have one wire meeting another wire. Then tunneling occurs through the skins of those wires, which is pretty cool. And in this particular case, you have a nucleus, and now it's going to produce an electron from the center of that nucleus. When it does, it converts a neutron into a proton, and that electron is going to tunnel outwards away from the nucleus. Yes?
Is it actually like teleporting, or does it just move so fast that it's...
That's a great question, and it turns out the answer is the former. It's actually not going through the intervening space.
So actually it's teleport.
It actually teleports.
Because it's possible.
Well, see, the reason that teleportation of something like humans would be impossible is that you would have to coordinate the teleportation of each single particle
It would be so hard.
such that they all end up in the same place on the other side. If you've ever seen Galaxy Quest, you know what that looks like.
And even then, would that technically not be the original you? Would that be...
Come together as some.
What is you exactly?
Wormholes.
What are you? I mean, if I cut off an arm, am I still me?
But then for a split second, when you have, like, none of your cells can join when you die?
You dead, and then you get brought back.
That's pretty wild. The question is, would you still have the same consciousness?
Yeah.
Would you have all your memories? Would you have, right?
Well, it makes you wonder if you have all your memories, but it won't be like you per se. Like, you know what I mean?
And could you tell the difference? If the new you has all the same properties as the old you, is it really a different you?
Or if you could 3D print yourself. It'd be a clone or something.
You can 3D print yourself, you just want to be alive.
What about wormholes?
Not
Are
yet.
wormholes legitimate?
Are wormholes legitimate?
Like, I know that they're
I'm going to
mathematically
pass on that
feasible,
question.
but
I'm going to pass on that question. I have no idea.
can they be?
Okay, so before. Now the nuclear radioactive event occurs, and what we're told is that an electron comes off, and also a small particle called a neutrino. And we are told the following things. The electron comes off with a momentum of 9.3 times 10 to the minus 23rd kilogram meters per second. And the neutrino comes off with a momentum of, I think it's 5.4 times 10 to the minus 23rd kilogram meters per second. And we're also told one more thing. These two are at right angles, at a right angle to each other. That's what we're told. And now they ask, what is the momentum of the nucleus after this event? The trick is just to draw it correctly. And once we draw it correctly, it'll be easy. So here we go. Because we are the problem solvers, we are going to choose the reference frame. And I think it's a good idea to choose the reference frame so that these two momenta that are at right angles are aligned along the axes. Doesn't that make a whole lot of sense? So we're going to draw our nucleus. Let's make this N star because it's the new nucleus with a little bit less mass. And we're going to have the electron coming off like so. And we're going to have the neutrino. The symbol for the neutrino is a nu, like that, with a 0. Well, the V with the curvy side is a Greek N. Actually, there are several different symbols for neutrinos. This is one of them. And this guy right here is going to have a momentum of 9.3 times 10 to the minus 23rd. Since everything in this problem is times 10 to the minus 23rd kilogram meters per second, I'm just going to represent the mantisses. And we'll put the 10 to the minus 23rd back where it came from at the end. So is everybody comfortable with how I've represented this? We've got the momenta at right angles. Up or down doesn't really matter. And we have abbreviated the numbers here so that the times 10 to the minus 23rd will be carried through to the end. Good? Okay. Now, gut check. Which way is this nucleus going to go? Bottom right?
Southeast.
Why?
Because one goes east and east.
Let's train the gut then. What is the total momentum before the collision? So what's the total momentum after the collision? 0. If these guys are carrying away momentum in this direction, then what direction does the nucleus have to go in order to cancel it out? It has to go northwest. So the nucleus is going to head off in this direction. The momentum of the nucleus is going to be on the south. That's just our gut check. Now let's actually do the computations here. The big idea, P0 equals P final. And the original momentum is 0. And we're going to go through and add up object by object. The nucleus plus the electron plus the neutrino. And now here comes the representation issue. The momentum of the electron I'm going to represent as 9.3 comma 0. 2 components because 2 dimensions in the problem. And the momentum of the neutrino I'm going to represent as 0 comma negative 5.4. This is the big deal to get this right. So are there any questions about this?
After this, you just solve.
And after this, you solve the PM. It's real simple. It's harder to describe the problem than it is to work it. So when I simplify, I get this. And now I'm going to subtract 9.3 negative 5.4 from both sides. So, and 0 minus this is negative 9.3 comma positive 5.4, and that is the momentum of the neutron, which is what, the nucleus, excuse me, which is exactly what they asked about.
That seems a lot less harder than it was.
It seemed harder, it seemed a lot less harder than it seemed. It probably seemed a lot more harder than it seemed. Let's see. Okay, how are we doing? Does this make sense? Awesome. I'm gonna have you guys get into pairs, 2, 2, and you and Matt can work together, Christian. And I would like for you guys now to tackle number 42. I'll pause this while.
Wait, did anyone get the problem?
Nope.
Nope.
So we have, what's the initial velocity, 1.8? Is that?
Yeah.
Yep.
Yes.
Okay, so this guy hits, and so your before situation should look like this. Your after situation should look like this. You've got your 0.4 going off at a velocity of 1.1 at an angle of 30 degrees with the horizontal, right? And you've got your 0.5, and we don't know exactly how it's going off. We'll call that V final for B, for object B, but it's going off in that direction-ish.
How was that even possible? How's
Well-
the ball gonna hit something from the right and then go to the?
You ever played pool?
Yeah.
Sure. Here's the easy way to see it. What's the total momentum of the system before the collision? Definitely that, right? Therefore, the final momentum has to be exactly the same. So if this guy is going to go off and up, this guy has to go off and down. See it? All right. So now, we construct initial equals final. And the initial momentum is easy enough. That's going to be 0.4 times 1.8 comma 0 plus nothing because the other guy is motionless. So therefore we get 0.72 comma 0 is the initial momentum. For the final momentum, I'm going to make this as easy as possible. It's going to be 0.4 times the velocity, which is 1.1 at an angle of 30 degrees, plus the momentum of B final, which I don't know. Does everybody see how that's a really simple way to capture that? And we do a little bit of multiplying here. This is 0.44 at an angle of 30 degrees plus PV final. So finding PV final is a matter of subtracting. Now finally I have to do my just-in-time computation. I have to turn that into rectangular form, right? R cosine theta, R sine theta. And when I do the math, I get 0.38, 0.22 plus PV final. Combination of cheating and having worked the problem previous period. The sine of 30 degrees is exactly 1/2, so that's easy. The sine of cosine of 30 degrees, root 3 over 2, or 0.866. Not what I had to compute. And so we get PV final by subtraction is 0.72 comma 0 minus 0.38 comma 0.22. Hang on until we're done here. And this gives me 0.34 comma negative 0.22 is the final momentum. And I'm going to represent that as mass times final velocity. And so the final velocity is therefore this divided by 0.5, which is the same as multiplying by 2. And there's my final velocity. And I'm done.
So you want us to do our cooking lab right?
I do. And I'll